So yesterday in the tutorial, we covered installing packages with Spack and using environments, running through the configuration of Spack, along with some other concepts. Today, we're going to actually look at, when we were installing and working with packages yesterday, we were working with those already, one built packages from the binary, but also we're using the instruction set that previous maintainers have already put into Spack. We call these like package.py files, and really there are a bunch of directives and metadata on your packages. So today, no matter if you're a developer or a sysadmin or a package maintainer, we're going to turn you all into package maintainers for a little bit through this guide and get working with some of the internals of Spack. So give me one quick minute. We're still waiting on a firewall rule to be updated. It's a little bit faster yesterday than it was today. If it doesn't go through here in a second, we'll just hop in and start walking through. But so I guess following the link that Greg sent out in the chat, which is the Spack VMs, you can go claim a VM, just put your name in the IP and the username that you're using. Once you do that, to get us back set up to kind of the point where we were yesterday, you can go ahead and run git clone. Again, we'll do a depth of 100 off of the v22 release branch. And then pulling from GitHub for the Spack repo. Once we do that, we'll need to source the script to get Spack into our path and into our environment. And then you can run Spack tutorial-y and Spack bootstrap and Spack compiler find, and that will get us set up all to where we were yesterday. So if you just copy those commands and throw them into your VM, once everyone has done that, we'll be just about set up. Okay, perfect. And the instance came up. So I'm going to go ahead and do those bootstrapping steps. So git clone depth equals 100. We'll do branch equals releases v022. And then https github.com spack.git. And then we will source that file. So inside of the Spack directory under share Spack setup env.sh. And then Spack tutorial-y is just a little shorthand we have here to get us set up to where we should be. This is going to do that mirror import for you. It's going to trust the keys for that build cache. And then we will, Spack bootstrap is going to install and configure Klingo, which is that logic solver and ASP for us. This happens when you do an install. We're just going to do it explicitly right now so that we don't slow down any of the installations. Quick check from folks. How is the size of the text both on the terminal and the tutorial next to it? We should be used roughly the same size. Okay, cool. I'm getting thumbs ups from folks, so that's great. Okay, so we are finishing up our bootstrap. So packages inside of Spack are really the fundamental blueprints for how we define and codify the build processes for compiling up these pieces of software from source into binaries on our systems. And Spack and the open source community is this huge advantage because lots of people contribute to our package base. It's not just us from Livermore, it's folks from kind of all over the place. Most of the packages at this point have not been created by us. And so we're leveraging kind of this community knowledge to build up these files and codify the build processes for lots of scientific pieces of software, and also just software that you would use in your daily life, right? Like Emacs as a text editor is inside of Spack. VI, a bunch of the core tools for GNU, all of that is inside of Spack. So let's go ahead
let me cut in with something quick because a bunch of people seem to have missed it. The Docker command in the instructions at the top, do not run that if you are in the VMs. That is for when you are using the Docker container that we publish and don't have access to the VMs that we use during a live tutorial.
Yeah, exactly. So don't run this command if you're on one of our VMs. That is for if you're doing this tutorial. So these docs will be up after we give this tutorial. You're free to go back to them. We won't have the VM spun up for folks, but you on your local machine can go run a Docker container, which emulates the same environment that we're running here on the VMs. So nicely said. Thank you, Greg, for catching that. So to get started here, let's go create another repository for Spack. So some folks asked about this yesterday. Spack has our built-in repository, but you can layer on repositories on top of that. So you don't have to redefine all of the packages inside of built-in. You'll still inherit from those, but you can define, closed source packages or packages that are specific to your organization in another repository and layer that on top of Spack. So we'll do Spack repo add. Spack root is our installation directory where we installed Spack to, so just where we just get cloned Spack into. Inside of there, we're going to do Spack var repos. This is where the internal repos for Spack live. So there's one called built-in, as I just talked about. That's where all of the standard packages that you would find if you're using Spack is. For this one, we're just going to create one and we're going to name it tutorial. And now when we create our packages for this tutorial section, we're going to add them into that tutorial repo rather than into the built-in repo, just so that we keep things separate and it's easier to clean up for future sections. To create a package inside of Spack, you're going to use the Spack create command. That's just simply Spack create. For this tutorial, we're going to use a piece of software called MPI Leaks, which is developed at Livermore. And to keep it separate from the MPI Leaks that is actually inside of the Spack repository, we're going to name it tutorial MPI Leaks. So you'll do Spack create -- name tutorial MPI Leaks. If you don't provide a name of a package, Spack does its best to guess the name of a package based off of something like the Git repository that you download the package from. So oftentimes you won't have to define this. Again, we're doing it for the tutorial to keep ours separate. And then we'll do https github.com LLNL MPI leaks. And we're going to grab, if you go to the GitHub page for MPI leaks or, another package inside of GitHub, really what you'll want to do is go down to releases here if you're installing from a tarball, and then you're going to look for the assets that something, one of these projects creates. So here we're going to download the MPI leaks 1.0 tar.gz, which is a tarball. And then we can just copy and paste that inside of here. So that would be MPI leaks releases, download the 1.0 MPI leaks 1.0 tar.gz for folks that are following along and haven't pulled up the website over there. And then we'll go ahead and create that package. This will drop us into a text editor right off the bat. And from there, we'll start talking about some of this boilerplate and then the directives here. So this package.py file, which is what we're sitting in right now, lives inside of our tutorial repo. So tutorial packages, the name of the package, and then package.py here at the bottom. We will kind of look over a couple of things here. First of all, Spack pulled the source for MPI leaks, and based off of the files contained in that, it detected that MPI leaks is an AutoTools package. So we're going to be building with AutoConf and the AutoTools suite of of tools to go and compile this piece of software. And we can see that we've got a doc string here, which represents our description of the package. We've got a homepage URL or a path to our homepage as well as our URL. The URL is where you're downloading the source from, so distinctly different from your homepage is where people can go and find more information about the package. The URL is actually the source download location. We've also got this maintainers directive, which we'll talk about here in just a minute, but this is how you can sign up to be a maintainer for Spack as part of GitHub so that when someone goes and tweaks a package, you can get a notification from Spack to say, hey, someone just created a pull request with the package that you contributed. Would you like to look over it and make sure that they're not doing anything that looks like bad practice to you as the maintainer? So from there, we've also got the license of the packages. And so the license really specifies, in a lot of these pieces of software on GitHub, define a license. We codify that here so that you know when you're installing the piece of software, if you're downloading something that is open source, source available, etc. We've also got a version directive, which we'll talk about here in just a little bit, but this is the version of the package. And then we take a hash of the source. And so this is really preventing man-in-the-middle attacks, making sure then saying, if that tarball changes in the future and we get a different hash by checksumming the source tarball, we know that it's been tweaked, and we probably want to fail because this isn't the version that we found and tested before. And we'll go through and work on those fix me segments in just a second here. If you are updating a package or you want to add another version to a package, we have a command called Spack checksum. And so if we want to get that checksum out of MPI leaks, just like we saw for version 1.0, you run Spack checksum tutorial MPI leaks, and then the version that you're interested in checksumming. So here we'll do 1.0 since that's the only release of MPI leaks. And you can see it's the text is a little big here, so it's wrapping the line, but it will print out that version directive for you. So you get the version and then the checksum, which we just talked about. You can then just copy and paste this directly into the tutorial MPI leaks package.py file if you were doing this for a version that doesn't exist. And then that will tell Spack, one, this version exists. It's trusted because I just got the hash of it, and it'll proceed. You can then go off and build that version like you would any other Spack package. So let's go ahead and test just installing this package right off the bat to see if tutorial MPI leaks works. Spack detected that it's auto tools package, so it should know roughly how to build the package already. A little bit of the spoiler for this tutorial is that it's not going to know how to build the package right off the bat, so we're going to do a little bit of debugging here. Spack is going to know that the package needs like the GCC runtime, gmake, all for building something up with AutoTools. But when it goes and it runs the configure script as part of AutoTools, so you can see here we've got a couple of phases. It's running auto reconfig, or if it actually needed to run auto reconfig, it would. And then we're running the configure phase, so that's running the configure file that is typically found in one of these source repositories. When it goes and it runs that configure file, you see here that we get an error that says it's unable to locate adept utils. We didn't define adept utils as a dependency of the package, so that makes sense. We'll go ahead and do that now so that we get that into the path here. So if you want to edit in an already existing Spack package, we'll just run Spack edit and then the name of our package. So tutorial MPI leaks. And this will drop us back into that editor. Again, Greg and I are a little bit worthless inside of VI, so I'm going to reset my editor to Emacs. And then we will reopen the package there. There we go. Perfect. So now you can see we've got our package. Let's start going in and tweaking a couple of these fix me statements. So first of all, the very first bit here is that if you go and you submit this package to Spack, you probably want to pull this boilerplate out, but it tells you, a little bit of this information in the tutorial, how to edit the package, how to try installing it just to get you off of your feet originally. And then any of these fix me statements. So for, the description of the package, we want to put something real in here. We typically would copy and paste this from the MPI leaks GitHub repository. So if you go here, they're going to provide a description for you. It is totally fine to take a description like that and copy and paste it into Spack. And just to make this fit a little bit more nicely on here, let's also go add a proper URL for our homepage. And for the homepage of this package, there's not like a proper website. So we'll just copy the GitHub repository so people know where to find it. They can look at the README if they want. We'll add ourselves as the maintainer here. So I'll go and remove the comment from that. And I will just assign myself as the maintainer of this package. So Alec BCS is my GitHub username. That's typically what we put in here as if you want to get, messages from GitHub, you're going to put your GitHub username into there. We can look, I don't know the license of, I believe this is just a BSD license. So we can say it is a BSD and it is checked by me. We'll go and remove any of those. And at this point, we've got like a pretty well set up package. This is something closer to what you would submit back up to Spack, except for we need to go add that dependency as we found when we ran the configure script and it failed. And then we might need to adjust these configure arguments to tell it where those dependencies are. As is right now, now that we've edited the homepage, the description of the package, if we were to jump back out of that package.py, if you run Spack info on a package, so we'll do Spack info tutorial MPI leaks. This will print out this will print out in a nice pretty form the description of our package, the homepage, basically all the metadata that we put in, where you can find the first version of the package, dependencies of the package, and any variants that we might create of a package. And then also that license that we just put in there. So you can do Spack info for a whole range of packages inside of Spack. For every package that is defined in Spack, it's a good way to kind of learn more about a package at a quick glance without jumping into and editing the UI file. So here, let's go and add that dependency on adept utils that the configure script came back and was grumpy about not finding. So we jump into here. We will add adept utils. Typically, if you're going into a repository on GitHub, they will define the set of dependencies somewhere in the README or in a set of like install, basically somewhere in this repository. Doing that, we can also tell that, so adept utils is required, call path is required, and MPI is required, surprisingly, for MPI leaks. So we'll go ahead and add all of those dependencies while we're here. Again, from yesterday, we can define MPI, which here is a virtual package. So we're not actually depending on a specific implementation of MPI, but they all provide that same interface, allowing us to then pick which one we want to use during the build process. So now that we've added all of the dependencies, let's try this build again and see where we get. So again, we'll try Spack install tutorial MPI leaks. Oh, oh, adept utils is misspelled. So we'll rerun and install from there. And we'll see now Spack is going to go grab all of those dependencies shown in the output here on the right. It's going to grab some certificates, Boost, which is a library, as a lower level dependency, basically to build all the way up to MPI and to adept utils and call path. And once this builds up, we are again going to rerun the process of auto reconf and then the configure script. Here, the configure script again is going to fail for us, which spoiling a little bit of it, but just to make up for a bit of time. There we go. Again, it's even though we have now added this as a dependency for the package and it got built and installed, it is not something that MPI leaks is finding automatically. And so let's go in and let's debug this build a little bit. The first thing that we can look at is you can see the full output of the build by looking at this file here at the bottom. So if we do a cat on that, we can see all of the output running the configure script. And you can see here at the bottom, unable to locate an adept utils installation. So at this point, we have a couple of options. One of them that is a good process to start with is to test this build process manually by going and manually running the configure script. And so here, we're going to look inside of this configure script. We want to see what the command Spack ran was. Okay, so it came in here inside of it ran the configure script, and then it added this prefix for where to install the package to. Let's go ahead and copy that prefix, and we're going to use it here in just a minute. So that home Spack, this will be different based off of the username that you're using for your instance. But now we can use the Spack CD command. Spack CD allows us to jump into the source directory for a package after we've downloaded it. So if we do Spack CD tutorial MPI leaks, this will go set up the stage for us if we don't already have it. Actually, you have to set up the stage by using Spack stage if you haven't done this before, but we've done the Spack build before. So this is just going to CDS into that directory. At this point, you can see our directory looks basically just like this repository because we cloned the repository, and then that is the directory that we end up here when running Spack CD on the name of the build that we want to do. So this is good. We could run the configure script here, but we don't have any of those dependencies loaded into our environment. To do that, we're going to run Spack build env, and then the name of the package. So here, tutorial MPI leaks. And then we're going to launch a bash session with the modified environment. So setting our path, man path, a couple of basically getting our environment such that it would be the same as the internal environment, the sandboxed environment that Spack is doing the build for, so that we can manually debug this build. So we go in and run that command. It will come back to us with a new environment here in just a second, which also messes with my prompt. But as you can see, we're in a new bash environment. And now we can manually run that configure. So if we run configure, we're going to do configure and then the name of our prefix in which we're installing Spack into, or that we're installing the package into. This to be the same, but so if you copy and pasted that prefix, you won't have to worry about this. Unfortunately, my terminal got rid of my copy when the figured, and then prefix equals, it's going to be, for me, Spack1. So now we can go and run this, and you can see that we get the same output from running this manually, unable to locate our adapt utils installation. And so let's look at, a lot of configure scripts provide help. So how do we configure an adapt utils installation for our build? We go run configure help. We can see there's quite a few options in here, but one of them that helps us specifically is with adapt utils and the path to adapt utils and with call path. So those are those two dependencies that we added, and to optionally include them into our build, we have to define these two flags. So let's jump back. We're going to exit out of that bash session, and we will cd outside of our outside of the source directory there, and let's jump back into our package for tutorial MPI leaks. Yes, I did tutorial MPI leaks. And here, we're going to add a couple configure arguments to the package. And so this is exactly those flags that we just saw in the output here, the adapt utils and the call path. We're going to add those as basically two flags to the arguments that we passed to configure here. So again, we will take out our fixme lines, and then we're going to set up this args as a list, and we're going to just use a couple of format strings here. So if you guys have used Python before, this should be pretty familiar. But we're really just passing in those flags. So you've got the name of the flag, and then we're setting it equal to self.spec is going to reference our current spec. So our current concretized, the name of the package and all of its dependencies. So inside of this, we look for our dependency called adapt utils. And for that adapt utils installation, we want to look at where it was installed to. So its installation prefix. So we'll reference self, our spec, inside of our spec, the name of our dependency, and then the prefix out of that. And that will let the configure script be able to go and find these dependencies. And we'll go and we'll do the same thing for call path. So again, just the name of the script, or just the name of the flag. With call path, our script or our spec here, the name of the dependency, which is now call path instead of adapt utils. And then again, we're just grabbing the prefix is just a variable inside of that object that links out to the location where that was installed and where other packages can find it. And from there, we will just return those arguments to our build. So again, let's do a tutorial or a Spack install tutorial MPI leaks. And this time, we'll have all of our dependencies installed, so we shouldn't need to install any new dependencies, but we're going to reload all of the dependencies into that environment, and then rerun our configure script. And we should see that this time the configure script, it succeeded. It found both call path and adapt utils. It built, and it successfully installed for us. And then you can see timers of how long each of those processes took. And we now have our new tutorial MPI leaks package. So this is pretty good for our base package. Now we might want to go ahead and add a variant to a package. So we talked about variants yesterday in the basic session. if you say that you want to Spack install, in our case, MPI leaks, you can do plus the name of the variant or tilde and the name of the variant. Plus enables the variant, tilde disables a binary variant. And then you can also have variants that take arbitrary values just by setting the variant name equal to a value on your install. So here, let's look again at that configure script or the help output of that configure script. And so we can just look for it over here. And there's two things here that we might want to add into a variant. One is the stack start value for C, and the other one is a stack start Fortran value. So to turn those into a variant, we will again go ahead and edit our tutorial MPI leaks package. So Spack edit tutorial MPI leaks. And inside of here, under version, but before we get to depends on, we're going to define a variant. And this variant directive is just variant, the name of the variant that you want. So for our case, we're going to call it stack start. It's going to accept any integer values as the name of our variant. So we're going to do values, any integer. If an integer or if the variant is not provided, we're going to default to having a stack start of 0. And so this really allows you to have variants that, have default values if folks don't define them, but can arbitrarily take values when provided by users. And then we'll also go ahead and add a description here. And that'll just be description and then the name of the description. We can steal this right from our configure script. And for this, I'm just going to copy and paste it from here. So we're defining it as specifying the number of stack frames to truncate in our starting value there. Now that we've defined this, we've defined a variant, and that variant is provided to us in our configure arguments in our build, but it's not actually modifying our build yet. So let's go ahead and add in a couple of sections here. So inside of our configure scripts, when someone defines stack start, so here we'll grab the value for stack start. It's going to be an integer as we know. We're going to do self Spack variance to go grab our variance out of there. And we're looking for a variant that has the name of stack start. We're gonna grab
You might want to go back up to your variant directive because you misspelled values.
That is a good point. Cool. So if we grab our value now out of the correctly stated values in our variant directive, we'll grab that value out and say, if that exists, if someone defined it and it's not 0, here we'll do if stack start to check that. If someone has defined it and it's not 0, then we will extend our arguments. So we'll come in here, we'll do args extends, and here we'll add another list. So this will be another set of f strings. So we'll do with stack start C for our C value for that configure script. And then we'll pass in our stack start value for that. And we'll again do the same thing for Fortran, and I will copy and paste here for time. But if you're following along, it shouldn't matter too much there. So now we're saying if stack start is defined, we're going to define these 2 extra flags that get passed to our configure script when we go and do our installation. And they will be passed in dynamically, whatever value we get as a variant there. We can keep the rest of this the same. So we'll go ahead and save and exit out of there. And now we can do a Spack install. We're going to do -- verbose here just so that we can see the output of the build. Tutorial MPI leaks. We'll do stack start equals 4 as our test here. So that's just setting our variant stack start equal to an integer 4. We'll go ahead and run this build, and we'll see, again, we're reusing all of our dependencies and just rebuilding the top level package. If we run through this configure script, wow, we misspelled something in there.
Extend versus extends.
Yes. Okay. Args extend. Go ahead and rerun that with our build again. And you'll see as we go through our configure script, we will be able to see that we set those stack start values in. So we can see for when we call adept utils, and then we're saying with call path, and then we've got our stack start for C and our stack start for Fortran there, both setting them equal to 4. So you can see now we're doing our build with those stack start values. You can see a lot of the output from make and compile. And again, we were successful there. So we went ahead and successfully built the package. Oftentimes when you're building packages, you also want to have a couple of sanity tests in there, right? Like we could build this package, but that means that we ran make and make install successfully. Often, a lot of the time, we might want to add what we call sanity checks to say, did we correctly install the directories, bin and all of the binaries that we expect into our prefix? So let's jump again back into our tutorial NPI leaks. Package.py file. And here we'll go ahead and add this sanity check for checking if the directories bin, lib, and char exist. Copy that without the space. And we're going to throw this right under that license directive before we get to our version. So now if we go ahead and rerun this build, again, for tutorial MPI leaks, we won't do the variant version of it. We'll just drop into our normal. And now that we have successfully installed this package, we should uninstall it so that if we just ask for it again as the same variant, it's going to reinstall, or it's going to say that nothing has changed for us. You already have this package installed. So let's Spack uninstall. We're going to say, yes, I want to uninstall it. And I know what I'm doing, so I'm going to do that -y. We're going to uninstall all variants of MPI leaks that we have installed so far. Thanks. Okay, so we went and we uninstalled both the one that we created with the variant and the plain one. Now let's do a Spack install. We're going to do test equals root. There's two optional values here. You can do test equals root or test equals all. Test equals all will run the tests both on the package that you're trying to install and all of its dependencies, whereas running test equals root will just run your tests on your top level package rather than all of your dependencies. This is a little bit faster, and typically, unless you're changing your dependencies, you can trust that the maintainers inside of Spack should have tested before they published an update to test the dependencies for any of their tests there. We also run them inside of CI. So if you're just developing a top-level package like MPI leaks here, we can just run test equals root. So again, this will grab all of the dependencies and it will run through the process of building tutorial MPI leaks for us. And at this time, after it does its build, its compile, and its install, it's going to go run those sanity checks. So as you can see, one of our sanity checks here failed. No directory in prefix char. Char is a typo, probably should have typed share. So again, let's Spack edit tutorial MPI leaks here. And if we come down here, oh, too far. Inside of this, we'll just correct that from libbin char to libbin and share. We'll save that and exit out of there. And let's rerun that installation and we should be set now. So this is, nice little way to say, I expect this package to output these set of binaries, these set of directories. And if it doesn't, for some reason, you should let me know. Like the build silently failed somewhere in there. It didn't compile as something it was supposed to, or it didn't get moved to the right location. And as you can see, now we successfully installed the package with our tests. So the last thing we're going to talk about here a little bit is some of the grammar inside of Spack packages. So to demonstrate, I'm going to open up tutorial MPI leaks here, but you guys don't necessarily have to. Just feel free to pay attention to the screen and we'll talk a little bit. So inside of Spack packages, oftentimes, if we're looking at if a package is younger or is of a lower, earlier version than say 1.1. In this example, we're going to say, you can say this for dependencies. So you could say that I depend on MPI 1.1 and anything later would be this example. Or you can say anything up to and including version 1.1 here. We do the same thing for inside a build. Say that your build processes changed from anything under 1.1, so 1.0 and anything lower than that. If your build process changed, so you have a new flag, you have a new argument, we'll come in here and we'll write if spec satisfies. So if you are a package or a spec and you're spec'd to be over 1.1 or 1.1 or newer, go ahead and do these things. Similarly, we can do this for compilers. We can say, hey, if I'm running with an older version of GCC, so a GCC before version 5, so GCC 4, for example, I need to do these extra couple of arguments on the build, or I need to change the build process a little bit. You can also do this for dependencies. So just as we saw when we added in the adept utils path and our call path, we can refer to our dependencies and query values about them by querying self-spec and the name of the dependency. And so we'll do self-spec name of the dependency here satisfies. We're looking for basically if I'm using, in this example, Dynast 8.0 or later, go ahead and use a couple of these new Dynast options that didn't exist before. We can also, for virtual packages like MPI, ask about specific implementations. So you can say, if I depend on MPI, the interface, but not a specific version of MPI, but if I'm building with OpenMPI, there's another flag that I need to set. You can go ahead and query that inside of a Spack package here. You can do this for any of the MPI providers, or really any interface for virtual packages that are defined by multiple providers. We have a shorthand here for variants, so that you can just say if your plus debug or if your tilde debug in the spec. So if I've added a variant or subtracted a variant, we didn't do that over here because our variant was multi-valued. But if this was just plus stack start and minus stack start, we could just do if stack start plus or tilde do one logical step or another. As packages change over time, we also see that a package might start out as an AutoTools package when it's early in its development, and then it might turn into a CMake package or a Ninja package later on as newer versions happen. So for example, Uncrustify here started off as an AutoTools package. So anything less than and equal to version 0.63 here is an AutoTools package, but then they changed their build system to be CMake later on. So we can define this. This is just another package.py file, and we can say, well, the build system is CMake for one, and so we inherit from CMake. It's AutoTools for another, so we also inherit from AutoTools. And then we can change the dependencies, and we can change some of the build logic in here by saying when your build system is equal to CMake. And we could specify the same spec as well. You could query your spec and say, when I have my variant that's build system equals CMake, do a couple of, output the arguments, do the build in a slightly different way there. So this is really a way to maintain, as we've had packages inside of Spack for a long period of time, those packages now have changed pretty significantly, and this is nice for package maintainers to unify those build systems. If you're getting really complex in your build, you might want to define two different builders for that. So say, hey, when I'm a CMake package, I define a set of CMake args. And when I'm an AutoTools package, when I'm earlier than version 63 or 0.63, go ahead and define the configure args this way. If I'm 0.64 and anything newer, then you're going to run through this code path and you'll use these set of arguments. But you can define them as two separate subclasses inside of your package and then define out the logic just like you would for any CMake package with your CMake args or any AutoTools package with your configure. To finish out the hands-on proportion of this tutorial, let's go ahead and uninstall all the versions of tutorial and PI leaks that we created. So we'll do Spack uninstall AY. So we're going to say all of the versions of tutorial and PI leaks that I've created. So any of the variants, I believe here we should just have the one, and then why I know what I'm doing, and then tutorial and PI leaks. Not even close to how you so. Okay, so we uninstalled the one version. We're also going to go ahead and remove our repository so that in the stack section, which Greg is going to be giving here in a minute, we won't have any of our legacy configuration from this part lagging around. So we'll do Spack remove tutorial. You can see it removed the repository with the tutorial namespace. So we are back to the configuration that we were just before. Packaging is like one of the biggest ways that you can help contribute out inside of Spack. We're always happy to help people debug new Spack packages and help contribute to Spack. So if there's not a package that you need, that if it's not already inside of Spack, feel free to start creating a package. Even if it doesn't work off the bat, submit it as a pull request to us. We're happy to help work with you on getting it up to being an installable package. And then you can start contributing to the repository and becoming a part of the community. I think it's a great group of people, and we try to get to all of the pull requests that we get within, at least a couple of days. We get a lot of pull requests, but we're always happy to help out. So with that, I will turn this over to Greg to talk about stacks.
We just talked a bunch about writing our own packages. Now we're going to come back to how do we deploy things to users. And for those of you who were here yesterday, or if you've done a Spack tutorial in the past or used Spack, you've probably looked at Spack environments. And the Spack stacks feature that we're going to talk about is really just environments with some combinatorial complexity to them. I want to install these packages for every combination of MPI and compiler that I care about. So that's what we're going to talk about. The first thing we're going to do is we're going to kind of set up our compiler and bootstrap our environment. And then we're going to turn off the view feature of the environment and focus just on what we're installing. So I've already done the setup here. I'm going to set my editor And now we're going to set up a compiler. So we're going to Spack env activate -- create. And that's just to create and activate at the same time. I am also going to add the prompt. Here we are. And we're going to build a GCC 12 built with GCC 11. We're going to run Spack env view disable. Right, we're going to put multiple different builds of the same package in here, so we can't have a normal Spack view. We'll come back to the view at the end to see what we can have instead. And Spack config edit, we can see, okay, what we've done is we've set view to false, and we've added this GCC at 12. So we're going to concretize that. And it's just one spec to concretize. We installed this spec as part of the basics tutorial yesterday, and we'll install it now. Now, if we remember from the basics tutorial yesterday, simply installing the compiler is not enough for Spack to use it as a compiler. So we're going to have to tell Spack about this compiler once we've installed it. And we could either put it in our path and run Spack compiler find with no arguments, or we can run this command with Spack location -I to get the location of it. Because we have an environment active, when we run Spack compiler find, it's going to put the configuration directly into our environment instead of into our user config, like we saw yesterday. So we're going to have to wait a second for GCC to finish unpacking. GCC is one of the slowest binaries to unpack and relocate. I'm not entirely sure why it is so much slower than other large packages. I guess I will start talking about what we're going to do next then. The next thing we're going to do is we are going to add to this environment, right? We've kind of bootstrapped our environment with the compiler, configured to use that compiler, and now we're going to start adding 2 different builds of netlib scale-pack, both with OpenBLAS, but with different MPI implementations to that environment, and see how unhappy that makes Spack. And then figure out kind of what goes from there. Any questions that I can answer while we're waiting on this? Okay, there's our GCC. So now we will Spack compiler find Spack location -I GCC at 12. We can confirm we got what we expected. And now we will Spack add these 2 specs. I am going to copy and paste them to avoid typos. and we're going to Spack concretize. And pretty quickly, we're going to get an error because we've put two incompatible specs in this environment. You can't have you can't have a unified environment with netlib scalapack built two different ways. And you see at the end, we get this nice advice. Consider changing the concretization. What does that mean? So the way that Spack concretizes, we looked at how in the basic section, right, when we built Trilinos with an HDF5 with mpitch, Trilinos was using the same mpitch, and you couldn't accidentally have multiple implementations of MPI in the same DAG. And that is true for everything that's being unified, except for pure build dependencies. Pure build dependencies go in a separate unification set and can differ from things in the link run unification set. You can see the diagram here that I'm pointing to. Here's the conflict that we hit, right, with OpenMPI and mpitch. So what can we do about it? We could either decide we don't need both of them, or we can say, okay, let's relax the constraints on this environment. We're going to say spack config add concretizer unify false. If we do a spack config edit real quick, we can see we just toggled this value. So we could have manually done that as well. And now we're going to concretize again. And now you'll see Spack spins up multiple processes because the concretizations are independent. We can do them in parallel, and we're going to get two separate concretizations of netlib scalapack. There's also this when possible option that does best effort unification, but allows things to differentiate when they need to. This option is somewhat tricky to work with. So it's great if you can get it to do exactly what you want, but it is, if you're using that option, you're kind of signing yourself up for figuring out a lot about exactly how your environment is put together and how that's going to interact. So let's expand this software stack out a little further because we might care about multiple implementations of LAPACK as well. So we could just keep adding specs with all this detail, but that doesn't seem like a great answer. So Spack has a better answer for this. We're going to spack config edit, get our environment back, and we're going to leave our GCC. But instead of listing all these specs out, we're going to create a matrix. And we're going to create a matrix where one of the dimensions is our packages that we want, which right now there's only one of them. One of the dimensions are our MPI constraints, which we've expanded out two of them. One of our dimensions are our new LAPACK provider constraints. So we want one built with OpenBLAS and one built with netlib LAPACK. And one dimension are our compilers. And there was only one compiler that we care about. We can get rid of the old ones. And this values in quotes because % is a special sigil in YAML. So if we have a string starting with a % sign, we have to quote it. So this matrix is equivalent to having written out 4 specs. So with so few, okay, maybe it's a win, maybe it's not to do it this way. But you can see how once we start adding 2 more MPI implementations and 3 more packages, this is going to start being a big win. So now we're going to Spack concretize, and it's going to concretize 2 more specs because 2 of the products of that matrix are the things that we had already added. So we don't need to reconcretize those. And 2 of them are new. The ones with netlib LAPACK are new. So let's look at what we got. We've got Spack find, and we can even Spack find -c, and we can see the concretized roots. Right, here's the 5 things are in our environment. So this is nice, but what if we need multiple matrices? Or what if we want to reference the same list of specs multiple times? What we need then is some definitions. And we can say we've got a list here. We've got a list of our MPIs. We want OpenMPI and MPitch. We've got our LAPACs, and we want OpenBLAS and netlib LAPACK. We've got our compilers. Well, all 1 of them. GCC at 12. And then we're going to name this MPI packages. And this is just our netlib scalar pack. And now we can come down here and we can say, this is our MPI packages. And here we have our MPIs. But notice I didn't write them as dependency constraints here. I wrote them as packages. So I can take them and turn them into dependency constraints when I reference the variable. I'm going to do the same thing with the LAPACs. And I can do the same thing with the compilers, turning them into compiler constraints. So right here, I haven't changed our environment at all. I've just created some variables and referenced them instead of hard coding everything. We can check that that won't change the environment by doing Spack concretize. Percent GCC. Someone sees my syntax error faster than I can. That. So I wrote the compiler as a constraint instead of as a package, and then I tried to turn it into a constraint again in the list. So I just needed to keep straight which one I was doing when. Concretize, nothing to update, right? We didn't change our environment at all. So now let's extend this sum. And this is why it's useful to create these definitions. We can say, we have a serial package that depends on LAPACK, PySciPy. So for our serial packages, we can create another matrix. Here's our serial packages. I'll fix my pluralization up here too. And it depends on our LAPACs. And it depends on our and it needs our compilers, but we don't need any MPI constraints here. And we can Spack concretize this, and we're going to get two specs for SciPy, one with each of the LAPACK implementations that we care about. And that's great and all, but another thing that we might want to do is we might want to construct this matrix and exclude some specific components. So we're going to actually come back to this matrix, and we're going to exclude something. We're going to say exclude pi SciPy depends on netlib LAPACK. Now, obviously, this matrix is getting a little silly right now because we're just doing toy-sized examples, and it's been whittled down to only one spec. So we could just replace it with that spec, but we're going to keep it as a matrix because we're focused on the syntax and not the size of this environment. So now if we Spack concretize, it's going to remove that one. We can see it with Spack find. There's only one SciPy. And now we're going to install this environment. All right, and it's going to take us a minute for this to all install. So does anyone have any questions on that? Let's see. What version of Spack adds stacks? Everything. I shouldn't say everything without thinking about it more, but basically everything in this section of the tutorial has been in Spack for a while at this point. I think stacks went in maybe 0.15, 0.16. So we're talking 4 or 5 years ago at least, for all of this functionality. So any roughly modern version of Spack, you should have access to all of this. I got a question also. Can Spack check whether the disk space required to install the entire stack is available? No, that is not something that Spack can do. We do not track the amount of disk space used by various packages. Is there a way to visualize the matrix? The combination of Spack concretize and Spack find that we've been using is how I visualize the matrix that I'm building up, or just Spack find without concretizing will help with that. All right, so we've got our environment installed. The next thing that I want to talk about is conditional definitions. So we come back here, right? All of these definitions are unconditional, but maybe we have conditional definitions. On some of my systems, I use GCC 12, and on others, I use GCC 13. On some of my systems, I use OpenMPI, and in some of my systems, I use MPitch. So we can have conditional definitions. The conditions that we use are a simple Python conditional that we write into the YAML code as a string and only has access to a very small set of variables. Those are the platform, the operating system, the target, and the architecture of the machine. and the user environment, Python's regex module, and the host name. So if we come out here and say Spack Arch, right, here's the platform, operating system, and target that Spack has for this machine. We have access to those in our conditions, as well as the triple with all three of them, the user environment, the host name, and regular expressions. So what we're going to try is we're going to say, I have a conditional set of MPIs for OpenMPI when, and then I'm going to copy and paste this. What is this saying? This is the Python code to say, get a value from this dictionary. If it's not in the dictionary at all, give me the empty string. And is that value equal to the string 1? Have we set this environment variable to 1? Now, the other thing to notice about this syntax is we've got two lists named MPIs here. If you have lists with the same name, they are concatenated. So we have an unconditional component and a conditional component. When this variable is set, we will have two MPIs. So let's take a look at it. Spack concretize and Spack find. And with Spack find, we see, right, we've cut down the space of our MPI packages in half. Now, if we export our variable, backstack use OpenMPI equals 1. And we're going to Spack concretize again. And we're going to get back to exactly what we had before. And you can see, right, all of these packages were still installed in Spack outside of the environment, so we get them back immediately. Okay. So now we've built up our environment. We can do a bunch of different things with it, right? We could push it to a binary cache. Todd will talk more about that later. We could fetch all of the sources for it to pass to an air-gapped machine. We could install it all really quickly with an environment file, but let's talk about deploying this to users. So we got rid of the view right at the beginning. Let's bring the view back. So what we can't do is we can't just set view to true, right? These packages are all going to conflict with each other when we land them in the view. That's not going to work. So there are two ways that we can work around this. One is we can say, let's choose what goes into the view. So we're going to say view default root. Default is a special name for a view. This is the one that gets put into your path when you activate the environment. And we're going to select everything built with GCC 12. So we're not getting any of the dependencies from GCC conflicting with things. And we're going to exclude our mpitch and our netlib laypack, so our default OpenBLAS, OpenMPI versions are the ones we get in this view. The other thing we can do is we can add complexity to the view. So we can create a different root, and we can say, I want to change how packages are mapped into this view so that they go into different directories and create space that we can have some combinatorial complexity in here. And so the way this works is we have a matching spec. Anything that matches this spec is going to get this path scheme. And okay, so we've got the compiler and the compiler name. We can use a caret to say, grab my MPI dependency and get attributes from it, etc. And often maybe you'd put the package and the package name in here, but we're going to say anything built with the same MPI and LAPACK is going to go in one directory. And then the way this works is that Spack is going to go down the list. So if you satisfy depends on MPI, depends on LAPACK, you're going to get this one. If you don't, and you satisfy depends on LAPACK, you're going to get the next one. And it's the same thing. We've just taken out the MPI components. And if you don't depend on either, then we're just gonna give the compiler information. That's the only kind of degree of freedom we have in our environment for that. Now, all is a special word in this case. It can go anywhere in the list, but it keeps it a lot simpler to understand if we just put it at the bottom so it's all fall through. YAML hates tabs, so that's why I've gone through and gotten rid of them. And we're going to concretize again, just to regenerate the views. So here's our two views. We can take a look at them. Here's our default view. It looks like a normal Unix prefix, like we'd expect. We can look in lib, and it's got all sorts of things there from our dependencies. And we can look in the full view, and we have things split by compiler. So there's one more thing that we're going to do with the view, though, is this view is a little unwieldy, and we probably don't care about all the dependencies, because Spack rpaths everything anyway. We should be able to find our dependencies. So we're going to say link roots. The default is link all. We're going to link just the roots. We're going to leave everything in the other one. So now we're going to Spack concretize again. And if we look in lib now, right, we get some lib entries from SciPy, some lib entries from ScalaPack, and we only have the packages that we care about. But if we look in the full view, we can look down into these directories. We can say, okay, there's our GCC. It's got some things that went into it directly, but then we've also got these subdirectories for our MPI and LAPACK things in here. All right, so there's views. This allows us to expose the software to users in the sort of combinatorial path that users expect without having to have them go search through Spack itself. The other way that we're going to expose this software to users is through module files. So the first thing we're going to do before we start talking about the module files themselves is we're going to Spack add lmod built with GCC at 11 to our environment. And we're going to Spack concretize and Spack install. And this is just to have a module tool available. We will demonstrate using lmod modules. Spack can generate modules for either lmod or Tickle. Spack used to generate modules by default for everything that was installed, until we did a user survey and discovered that we could not find a single user who used the default configuration, and we could not find a configuration that a large portion of users would like. So we turned off the default generation and said, well, if everyone who's using modules has to edit the modules config anyway, we can enable modules when we edit the config. So we're going to source lmod. That's dot for source. We're going to get the spack location -i lmod /lmod/lmod/init/bash. And now we've got modules. Okay. So now we're going to configure our spack.yaml file to generate modules. Here's our file. We're going to jump down to the bottom. And we can have different module sets associated with an environment. We're going to choose the default module set. We are going to enable modules. Like I said, they're not enabled by default, and we're going to enable lmod modules specifically. We're going to set the root to be the relative path modules within our environment. We could set that to an absolute path if we preferred. And we're going to set up the hierarchy, right? lmod is hierarchical modules. So by default, Spack is going to put the compiler in the hierarchy. We're going to put MPI in the hierarchy. That's the classic lmod hierarchy. And then we're also going to add laypack to the hierarchy. So with Spack, you can generate more complex lmod hierarchies with any virtual package as a component in the hierarchy. So now let's actually generate some modules. When modules are enabled, Spack will generate a module for each thing as it's installed. But since we didn't have it enabled before, we're going to say Spack module lmod refresh to regenerate the modules. Yes, we want to generate all these modules. And now we're going to module use the location of these modules, right? It's our current working directory. Stacks was our environment. Modules was what we gave it. And then we get this architecture-based module hierarchy. So now if we do a module avail, we can see all of our modules here in core. If we module load GCC, we can see now the things built with GCC are available. This is the classic lmod hierarchy. These aren't great modules, though. For one thing, the hashes in the names make them hard to read. For another thing, we have a bunch of modules generated for things that we don't actually care about. Like, we don't need to module load GCC runtime for the runtime components of the GCC compiler that built the GCC compiler that we actually care about. So let's fix this up a bit. Sorry, I just scrolled off screen here. So first thing we said was a problem is we want to get rid of that hash. So we're going to set the hash length to 0. No hashes. And we're going to include our GCC package and exclude %GCC at 11.4.0. So these two lines combined say, get rid of everything built with the system compiler. We don't actually care about those. We want just the things that we bootstrapped on top of that ourselves. But we do want the compiler itself that we bootstrapped. We're going to say all for every package we're going to set an additional environment variable. So for our GCC package, it's going to set GCC root, and it's going to set it to the package prefix. And these names will get automatically uppercased in the key for an environment setting. Now, it's not just all packages that we can set things for. We can also set things for a specific package. So we're going to set a couple of environment variables for OpenMPI. I'm going to copy and paste the environment variables themselves. But right, we've got some handling for Slurm and some handling for OpenMPI itself that they need these extra environment variables. And the last thing we're going to do is we're going to set some projections. Now, this is the same syntax that we see up above for the view, but because we've made our hierarchy have MPI and LAPACK in it, we don't have to worry about those. And we're just going to set it to name/version. In fact, that's actually the default, so we could have gone without setting it. All right. So Spack module lmod refresh, which we saw before. We can add the -y flag to do it automatically. And now we have to add delete tree, because we're not just adding modules and we're not just changing modules that already exist, but we actually have to delete some modules that Spack wouldn't otherwise know to even care about, because we've changed the configuration to remove some of the module files. And presumably that means that I got some indentation wrong. Stacks / spack.yaml. So what did I do? All of this is supposed to be under lmod. So I'll fix my indentation. And there we go. So now if we do a module list, we currently have these old modules loaded. So I'm going to do a module purge. None of those exist anymore. Module avail. Okay, we see our GCC and the things built with GCC. And if we load open MPI and OpenBLAS, we can now see we get these extra sections, having GCC, having OpenBLAS available brought us these, having OpenMPI and OpenBLAS both available brought us these, all of them dependent on the compiler. So that's a very quick version of module files in Spack. There is a longer tutorial that we are not going to have time to present if you want all of the nitty-gritty details, but this should be a start for how to handle module files. And then with that, that concludes the stacks tutorial. So we talked about adding combinatorial complexity to an environment, and then how do we expose that environment to users in a way with either the view or the modules that helps users navigate that combinatorial complexity. So with that, we are done with the stacks section.
A question in the chat. Is there a way to remove the OS from the module path? For example, I always get Linux on Linux 8, x86, 64, v4 at the end of my path, even though I don't specify it in the absolute path.
If I remember correctly, there is an argument that allows you to do that. The reason I'm hesitating a second is because I'm not actually certain whether my pull request for that went in. So
I'm looking. It looks like it did.
Yeah. So there's this Arch folder property. What we're looking at right here is the validation schema for the modules config file. So you can set Arch folder to false, and you will get rid of that architecture specific subdirectory. There is not a way to manage it at a finer granularity than that. All right, I am going to move on to the next section of the tutorial, which I am also presenting on developer workflows, and I will let Todd and Alec handle any more module questions that come up. So now we're going to change gears a lot. We just talked about I am a sysadmin, I'm a facility staff member, I'm a team lead, or a team build engineer, and I'm deploying software for a bunch of users. Now we're going to go to the opposite end of the spectrum and talk about I am a developer, I want to use Spack for myself. So I am going to de-Spacktivate my environment, and we're going to talk about being a developer. So the Spack install command we've talked about a lot. Fetches source code from a mirror or from the internet and installs from that. And that's great for an end user, but that's not great for a developer. As a developer, we're working on a package. We want to have a tight iteration loop between changing the source code locally and testing that code. But it would be nice if we could have that while also having all of the nice things that Spack does to handle our dependencies. So that's what we're going to do. We are going to create a new environment. We're going to call it develEnv. We're going to cd into there. And we're going to create an environment there and activate it. The first thing we're going to do is spack config add packages, all variants, no Fortran. And this is just so that our builds go fast. For this section of the tutorial, we're actually going to have to build from source. So we're going to turn off some options to make the big builds go fast. And now we're going to Spack add MaxIO plus SCR. MaxIO is an IO proxy app. SCR is a checkpoint restart library. And we're going to be developers of SCR, but we're testing the integration of our code into a proxy app. So let's install this real quick. And so this is what we've done before, right? This isn't going to be a developer build. This is going to get source code from the internet and build it, or it's going to find a binary that we've already created and install from that binary. It's not going to be using anything that we've done locally. So here is a dependency graph for MaxIO without SCR. And so now what are we going to do next? We're going to tell Spack, hey, instead of handling SCR the way you normally handle a package, treat it as something I'm developing. So we do that with the Spack develop command. And the Spack develop command has slightly different requirements than the rest of Spack. For one thing, you have to manually specify a package version. Right? Usually, Spack will figure out a version and get the source code for it. If you're giving Spack the source code, you have to give Spack a version number as well. The other thing is that the spec has to be in the environment already. Spack's not going to figure out, oh, you want to develop SCR and you have MaxIO, I need to turn on the plus SCR variant so that SCR makes it into the DAG at all. If it's not in any of the packages you care about, it's just not going to be built. And then you're going to have to reconcretize the environment because there's a dev path variant that needs to be added to track this build. And you need to reconcretize to get that. So we're going to Spack develop SCR at 2.0.0. And we can grep just to look at what we've added. Here's what we've added. SCR, we've added it, we've set the spec, here's the version. We could also have specified a different path, but we're fine with the default. And if we look, Spack went out and got the SCR source for us and staged it right here. Now, we could have also said, hey, I already have the source somewhere. Here it is. I've got it. But we didn't already have it, so we let Spack download it for us. Now, I mentioned we have to Spack concretize -f. And we're going to see a dev path variant added to the SCR spec that we concretize. Now, this is important because, right, Spack wants to track the provenance of everything that we've built, and when we're making arbitrary changes, we don't really know what source we've gotten, but we know where it came from. And this directory is, in some sense, the unique identifier for the source changes that I've made as a developer. So now we can be developers. We can go and write code, break things. We can edit scr/src/scr_copy.c. Because yes, that is the name of it. I see my typo now. .c, not dash. .y. And just quickly for a tutorial, the best way to approximate development, in my opinion, is to forget a semicolon. So I went into this file, I deleted the first semicolon so that we can demonstrate what it looks like in a development cycle. So we're going to Spack install. And there we go. It broke. That's to be expected. If we edit it again and put the semicolon back, there it goes. And it's built correctly. Now I realized I just skipped a step in the tutorial because I wanted to demonstrate how this does iterative builds. So I'm going to just go back and do this again. Right, we have this exact spec for SCR already installed. And normally, if we install it again, Spack would say it's already installed. But because we've set it up as a develop spec, Spack will actually check the modification time of the source code versus the install time of the last install. And if we've made changes, Spack will just automatically install it over again. And of course, back and forth again. So how do these iterative builds work? I mentioned checking the source time. It's going to work out differently depending on your build system. If you just have a make file, no higher level build system, it's going to work pretty well. Make does a good job of tracking what's been done so far, what hasn't been done yet, and picking up where it's left off. Same thing with CMake, right? CMake has a CMake cache.txt. It will know if your CMake flags didn't change. It will redo things quickly. If you're using autoconf, rerunning autoreconf or rerunning configure modifies the file time of config.h. You get the whole rebuild all over again. So depending on your build system, you get nicer or less nice iterative build behavior with Spack develop. So another thing that we can do with Spack develop is we can be developing multiple packages at once, right? Okay, so maybe before we were fixing a bug with SCR and confirming that that bug resolves the bad behavior we were seeing in Max.io. Now maybe we're making a change to SCR that's going to require API changes in the calling code. So we can say Spack develop Max.io at 1.1. And again, this is going to download it for us. We could give it a path to download it too. We could give it a path and say, don't clone it, I already have it. But we don't already have it. So we're downloading it, and now we've got Max.io in this directory as well. Again, we have to Spack concretize-f because we've changed spec. We could Spack deconcretize and Spack concretize if we wanted to only modify the one spec, but concretize-f works just fine. And now all of the nice things that we got from having the dev path variant, right, here we go, are true for Max.io. And we would have to rebuild Max.io again to build from our local source, but it's built against, if I can find SCR in here, our already built SCR from our local source that we've been developing. And one of the nice things with this is we can take this and very easily pass a workflow to someone else. So we've got our environment here. We can make dir val other. We're going to cd into there. we're going to copy the environment over and activate it. So now we're in the new environment. And if we just run Spack develop with no arguments, Spack's going to say, okay, well, you don't have a copy of MaxIO at this location, you don't have a copy of SCR at this location, and your environment says you're going to develop them. So I'm going to set that up for you. And now we've effectively handed our developer environment, in this case, from one directory to another, or from one user to another. So now if we Spack undevelop both of them, it's going to remove them from the environment, or it's going to remove the develop information for them from the environment, right? We're not going to get rid of your source code. But now if we edit this environment, right, we've got empty develop information here. I saw a bunch of questions come in about Git workflows with this. This is most valuable for packages that have a Git attribute on the package. So if we say Spack edit SCR, right, we know what Git repo this comes from in Spack. And so if we say Spack develop SCR at develop, right, now we're working with the tip of the develop branch, and we can commit and move along this branch as we go. There was also a question about tests. All of the testing stuff that Alec mentioned earlier for running tests with a package, you can run those, right? You can say Spack install --test equal root, and it'll run the tests. And you can do that whether you're developing or not, although I would agree that it's more valuable as a developer than when you're using the main install method or the main released code. So that's a quick bit on Spack developer workflows. And I'm going to turn things over now to Todd to talk about binary caches in Spack.
Okay. So if you come in late, or if you just joined, remember to follow the instructions at the top of the tutorial setup up here. Spack tutorial-y will probably get you most of the way there to being where you need to be to start this. We're going to talk about binary caches. So you've seen a lot of use cases for Spack. One of the, in my opinion, coolest ones is that it can cache builds and reuse them over time so that you don't have to build everything from source. And Spack has binaries that you can install in your home directory. They're relocatable, and you don't have to have things installed in particular locations on the system. So we're trying to make it easy for developers to leverage these workflows and within their team of people who might be working in different locations on different systems. So we used to do this tutorial where we showed how to make a binary cache in the file system, and you can totally still do that. This is a relatively new version where we are using OCI container registries to store binaries. So these are becoming increasingly common. GitHub has one built into basically every account. Container registries are kind of interesting because they don't just have to store containers. They can store basically any kind of blobs that you want to push into them. And so in Spack 0.21, I guess about last November, we released OCI container support, which allows you to use an OCI registry basically as a build cache. And it you can store this in an OCI registry. You can store it in S3. You can store it in Google Cloud Storage. But OCI is nice because I would say it's the simplest one to set up. And we're going to show you how to do that. So let's install Julia here as our demonstration package. You can tell this was written by Harmon because Julia is the demonstration package. So I'm going to go in here and copy this command. I'm going to shorten what they did there. Spack and create dash with view, and I'm going to call it my env. Just make it right there. And note, you don't have to do all this. You can just replace this with the name. I'm going to cd in there. Oops. Really? I have screwed this up. Let me try that again. It's interpreting view as my env as a name, so it made a managed environment spec. rm my env. Get rid of that. Yes. And I'm going to try that whole thing again. Sorry. All right. So I'm going to say /my env, and it's going to create it right here. All right. So cd my env. And now I've got an environment with a spack.yaml. To use this, I'm going to go and add Julia to it. Spack-e.add Julia. And if I cat the spack.yaml, you can see that got added. There's Julia. And I'm going to go and install the whole thing. And I need to run Spack tutorial -y just to make sure. Okay, great. So right here, I'm going to go and install this whole environment from the build cache. It may take a little while because it's got to concretize Julia and go and fetch it from our build cache that we're using for the demo. All right, there we go. So there goes all that. Getting to open blahs. Only 9 more packages to go. What instance types did you end up provisioning out? Are they 16x larges this time?
We went with 8x larges this time.
Okay, cool.
They were sufficiently big that I think that people weren't gonna mess up on. Like 8x large is actually 16 cores on a C6A.
Okay.
But it was
Here's our vCPUs.
vCPUs.
Yeah, those are hyperthreads. But okay. All right. Here we go. Julia 193. It's finally installing. It's way better than yesterday with the lag. All right. So now I've got a Julia environment. And if I run the Julia that got installed here, let's see. Oh, I see. We go back here. The view is out here. I'm not following the instructions from the tutorial, so everything's a little different. We go to /view, bin, Julia, and I'm running that. It works. I can run 1 + 1 = 2. All right. So if we want to share what we just built with other users, we can go and make a package registry on GitHub to upload the packages to, so that someone else might be able to use the same build cache. And so we can do that together. I'm going to go to this page here. I'm already going to try to open a private window with our custom GitHub account that we have for making tokens. And if you go to github.com/settings/tokens, you should see a screen that looks like this. And I'm going to go here and generate a new token for general use. And what this does is it gives me permissions via the GitHub API to interact with GitHub in certain ways. And so I need to give it write packages permissions. And so that lets me upload packages to the GitHub package registry. Also lets me download packages from the GitHub package registry. And that's really the only permission I need. I'll just name it build cache tutorial. And yeah, we'll make it expire in 30 days. So actually, let's just be we'll make it expire in a week. And we'll generate the token there. Okay. And so you should get something like this. I'm going to copy this token, and I guess I'll put it in the WebEx chat other folks can use this if they want to. Let me see. Here's the chat. And if you want to go through the tutorial and follow along, it's designed so that everyone has basically the way that we name the build cache in this tutorial is set up so that you include your username so we can all use the same account. All right, so that's created. And then we go back over here. And now that that's done, I can go and add this token to my mirror configuration in my environment. So I'm going to go into my env here, and I'm going to say spack-e dot mirror add OCI username, and my username is spack-tutorial, and OCI password. I'm going to just paste the token here. You can do this lots of different ways. So we can embed the password somewhere else. Unsigned for now, and I'm going to call it my mirror. And then I'm going to make a URL. And so this here is the URL for the build cache that we're going to use. It doesn't have to exist yet, but we can push to it regardless of whether we've created something on GitHub or not. And right now the GitHub user is Spack tutorial, and you can use that same user. I'm going to call it build cache, and then I'm going to call this tgamblin because it's mine. I'm doing the demo, and I don't know, I'll just call this Spack2. I don't know exactly what my host name is, and I think that's fine. As long as you use a unique username here, you should be fine for the tutorial if you're following along. So now I'm going to do that. And now I've got that configured in my Spack.yaml. So if I edit this, you can see it. So here I've set up a mirror. It's got this URL. It has this access pair where you've got the username and the token, and then it's not signed. So we're just going to push it straight to the registry, which is pretty common with container registries. People tend to just trust the host rather than signing things like we do with binaries normally. All right. So we've looked at this. We've seen that the Spack.yaml has that in it. I can actually go and push to this mirror right now. So Julia's already built. It's installed. If I run stack find in this environment, then I can see all this stuff. Here's Julia right here. If I basically just do spack-e dot cache push my mirror, it's going to go and upload all of these things to GitHub. And you can try this too. So see, it's telling you the shot of everything that's uploading, and those go into the registry. So let's wait for that to finish. And waiting. It's a lot of data, so we'll have to wait a little bit. And it's not exactly all that fast. It's like, what, 62 megabytes per second there? All right. So now that that's done, it said, okay, I pushed all those packages. And now we can go over here to GitHub. And you can see here on your account tab in GitHub, and you can do this as your own user too. There's a packages 10. So if I click on that, what am I seeing? I should see it here. Yeah, like.
Yeah, you might have to reload it and wait for a second, but it should pop up there.
Okay. That's a little weird. So it's Spack tutorial. That's me. I made a token as this account. I go to the container registry. It is a little weird that it's not showing up here.
It's showing up for me, so I think it's a cache hit problem for you, or you have the cache loaded.
That is super annoying. Okay, I'm gonna try it in a non-private window, just as my regular GitHub user.
And it probably won't show up if you're not logged in because it's still technically private.
If I'm not logged in as the user, okay.
Yeah,
Can you share and show the window as your user just to prove that it worked?
Yeah, sure.
Yeah, why don't you share since you can actually see it? I have not seen that one before.
Okay, sure. So this is this is underneath the Spack tutorial user. If you go into packages here, just like Todd was showing, GitHub recently changed to being a React app a little while ago, and it tries to do a whole bunch of fancy cache stuff under the hood. And but you should probably see these pop up. They're private by default unless you go make them public. But if we wanted to make this one public, you can go click into package settings here, change the visibility, and make it public. So if we wanted to make it Tom's filter.
Yeah. Oh, no, actually, you know what? Hold on. I got it.
Okay.
I figured out what the heck the problem was. Here we go. I'm not logged in this tab. That's why. Over here in this tab where I made the token, I am logged in. So if I go over here to GitHub again, and I go to github.com/Spack-tutorial. Now I can see the packages. There we go. Okay. So here's the one I just pushed. Build cache tgamblin Spack 2. And it looks like someone else also pushed something. You can see all the different image versions in the container registry in here. And so you've got curl, you've got Julia, and you can see there that it says you can Docker pull this thing. So that's actually kind of interesting. Let's go back to the tutorial for a little bit, and we'll talk a little bit more about that. Okay. So now that we've pushed that to the build cache, we can actually install from it. So if I wanted to use this in my Spack.yaml, or actually, let me see. If I do git config or Spack config blame mirrors right now, you can see that I've got, I only have the Spack public mirror registered right there. And I have the tutorial mirror registered right above that. For this demo, I don't want to use the tutorial mirror because I know that it already has Julia in it. I want to make sure that I can install directly from the GitHub mirror. So I'm just going to demo that. I'm going to edit my Spack.yaml, or actually Spack config. Edit will do that for me. Oops. Oops. -e dot config edit. And it's in Vim. Give me a second. That should really. Sorry, folks. I like Emacs. All right. So I'm going to go in here. And I'm going to go and just add one extra colon here. What this says in our config, as you learned in the config tutorial yesterday, is override all the other config. So don't inherit any config from other scopes. So basically what this is saying is I only want to use this stuff. Don't use stuff from outside my environment. So now if I do Spack config blame, I can see that in this environment, I've only got this particular mirror registered. All right. And so now if I do Spack-e dot install dash overwrite Julia, it says, yeah, you'll reinstall that one. And it says, okay, see how it pulled it from the actual container registry there? So it fetched from ghcr.io, which is GitHub's container registry. And it grabbed the build cache image and extracted Julia from that binary cache. And it just reinstalled the same thing again. So that's pretty much all there is to it. If you want to share binaries with someone else, you can build it, you can push it to a remote mirror like this, and you can have someone else put the same configuration in to their YAML to basically fetch from that build cache. So what we're hoping is that this makes it really easy for people to share binaries. All right. So if you do want to do that and you want to make things available to your team, there are a couple of other steps that you have to take. So to reuse binaries, like we learned yesterday, the concretizer has to be able to fetch an index of what's available. And so we have to upload an index to the mirror in order so that it has basically a JSON file in it that tells Spack what's available. So if we run that, it goes and fetches all the information about the binaries that are there. It's basically fetching all the metadata, so all the specs for all the packages in the mirror, and then it goes and uploads an index to the here. And so once that's done, you'll be able to use it for reuse, and you'll be able to run build cache list with it. So now if I want to list that that build cache, I could say Spack -e dot build cache list for all architectures, and it'll show me what's in the build cache. And this is the same sort of output that Spack find would give you for looking at what's installed locally. It's just showing you what's in the remote build cache. So like there, and you can see that like even the hashes are the same. So if I run Spack find -l here, this autoconf locally is, or well, I'll run it for this environment, Spack -e dot find -l Julia. If I run that, I can see there's my local Julia. And if I run the build cache list, it's the same Julia that's up there in the build cache. So I can remotely query what's there using that command. All right. So we talked about how over here in the GitHub package registry, each of these looks like it's its own container image. And in fact, like that's pretty much how we are storing the packages. Each one is stored as basically a container layer, which is a file system image that has all the files that go into that package. What they don't currently have is a base image, and we can do that. We can add a base image to the binaries that we push to the build cache, so that they're runnable as Docker images. If I try to run, let's try it now. So is Docker on these? I believe it is, right? Yeah. It may take a little while to run the first time. Yeah, there we go. Docker's working. Okay. I can go Docker run ghcr.io/spack-tutorial/ build cache -spack2. And then if I grab the Julia image that I know about over here, I guess I could have copied and pasted this from GitHub. If I go and run that, it's going to say that there's an error. It's unauthorized. That is the error I'm supposed to get, right? Unauthorized.
Yeah, because you're not logged in.
Yeah, that's right.
And it's not public. So you could do Docker login.
Yeah.
And the username and Spack tutorial, not a TCAM one.
Well, no, it's Docker. Docker login to GitHub container registry is what you're saying.
Yeah. So Docker login.
Yeah.
HCR.io.
And did you make it public so I could actually fetch it from my own personal account?
I can do that.
Yeah. Okay. I don't want to do the 2-factor on the other account right now. No. Oh, is it going to correct it me because I don't have a token for the other one? Actually, I have the token, right?
You do have a token.
So I can log in with this.
If I just make it public for you, though, you shouldn't need to sign in.
That would be great. Let's try that. I want to get the right error message. Yeah, okay. Yep, okay. So now I get the right error message. It's not unauthorized. It's manifest unknown. And so it's telling me that because this is just, currently this is just a blob of files in the file system within the image. It's not a runnable OS image like a normal container would be. And so to do that, what we can do is we can go spack-e dot for this environment and do a build cache push and force it to override that. And we can give it a base image of our favorite OS. And so I guess we'll give it the one that we built on here, Ubuntu 24.04, and push to the mirror that way. And so it's going to do the push again, but this time it's going to add metadata saying that it should use that particular Ubuntu image as the base. And essentially what that means is that the Spack package is going to get overlaid on that OS. All right. And so now it's trying to push all that. I think this can be somewhat slow. Here we go. And it's starting. Any questions while we're waiting for this? I wonder why it's so slow this time. All right, there we go. That's pushing everything you can. All right, that was faster. Okay, cool. So now, if I go and pull that image again, what am I trying to do here? It should be there, user.
Hash changed.
Oh, that's right. Okay, yeah, because okay. The hash changed on the yeah. Okay, let's go grab the actual hash on the GitHub side. Refresh this guy. Yeah, there's the new Julia one that has the base image in it. All right. Grab the new base image there. Yep, you can go and pull that. Now it has the whole thing. And I can go and run this thing. Where's my run command here? Oops. No, I want this one. Okay, I'm just gonna try and flip it. Oh, Julia. All right. All right. So now, oh yeah. I can run it, but I gotta do it the right way. Like that. And I'm running Julia inside the container. And so that's a very quick way to go and create binaries and push them to GitHub and to make them available either as a Spack build cache or as container images to other folks. I could also go and run batch in this container. And you can see like there's, I'm not actually sure where it puts the Spack binary in here.
I think it's under opt. Oh, never mind.
I'm not sure what Harmon made for the layout. It may just be in bin.
I believe it's in bin.
Yeah. Nope.
You do which Julia that could.
There we go. It's in home, Spack 2. Oh, it's exactly where I built it because I didn't do anything special with it. It's just adding that to the path. So there you go. So it's because we built in this path, home Spack 2, Spack house, Spack Linux, Ubuntu 222, blah, blah, blah. On our local machine, that's actually where it shows up in the image. That makes sense. So and if I go in there, you can see this is the Spack build that we made inside the containers. And it has all the Julia files and everything for the install. It's the same as what was local. All right. So if I go into the next section, if we want to add Vim to the environment, we could easily make a container that contains both Vim and Julia. So let's go in here and say Spack -e dot add install -add. That's going to add it and install it. Vim. And it's going to concretize Vim. And in this case, it's actually building Vim. So I'll just let it do that because we don't have the tutorial mirror registered for the environment. I didn't read the note carefully enough, but that's okay. Vim is pretty fast. All right, there's Vim. And now I can go and push the whole environment and tag it with a label that's descriptive. So I can basically do the same build cache push command I did before. Push, and I don't need a force this time. And I'm going to keep the base image, but this time I'm going to add -- tag Julia and Vim. and I'm going to call it, I'm going to push it to my mirror. So if I run that, it goes and pushes all the stuff. Most of it should be there already. It's basically pushing the entire the contents of the environment. And it tells me that it didn't push parts of them because they were already there. So now if I want to run that, I can say docker run -rm-it. Actually, let me get my previous run command. Previous run command there. And this time, instead of this long hash name, I can just say Julia and Vim, and just run that with a default entry point. It's going to download the container. It should pop me in a root shell. So it's pulling all that down. And now I'm in here. So now if I do which Julia, it's there. If I do which Vim, it's there. I can run Vim in the container. And you can use this basically to package up anything that you can put in a Spack environment and to push it to a registry, both for people to use as containers, or you can just use it as a build cache to collaborate with your team. And we're kind of showing both in this tutorial. And so this is going over the difference between using OCI build caches and using Spack containerize. So we've had a command called Spack containerize for a long time, which has the advantage that it generates a Docker file that you have to build yourself that does a multi-stage build. And that's still good. The nice thing about that is that the container can be smaller. So you can actually use Spack containerize to generate something that looks basically like this, where you start with a particular base image, it goes and copies in the spack.yaml, installs the whole environment, and then copies out the things that it needs from the base image into a new image. And so it basically avoids having to use all the build dependencies. It'll actually do a Spack GC in there to garbage collect all the stuff that's not necessary for the runtime environment. This requires that you run Docker build yourself. And so the real difference here is that when you're pushing to an OCI registry and using a base image, Spack's building the layers itself. It's basically building up the dependency structure and building the file system image itself. And you don't even have to do a Docker build or run Spack in the build environment. But we do have this Spack containerized thing as an option if you want to make a container from a Spack environment that with a known Docker file to build with. So there's a trade-off between those two. I'm happy to answer questions about when you would use one versus the other, but just keep that in mind. All right. The final thing that I'll note is in this tutorial, we demoed building an environment in this in our home directory. So I'm in home Spack 2 in the Spack installation that lives there, and that's fine. But the binaries that we create there are only going to be able to install into paths that have prefixes that are this long or shorter, or at least, you can try to install them into longer paths, but you may see issues because it won't be able to change all of the embedded strings in the binaries that might need to be longer for other paths. And this is one of the complicated things about dealing with binaries. When we do source builds, we can generate a whole new binary and it might have different strings in it. A lot of programs will embed the path to their prefix in their executables and in their libraries. And so what we tend to do in order to make binaries relocatable is we add this config option to the build environment. And so you can say spack-ee dot, so use this environment, config add, and it's config install tree padded length 256. And you can set this to different lengths. You could use 128, just something long enough that it's longer than the longest path that you would ever want to install the binary into. And what that will do is, instead of a layout like the one here, where it's in home Spack 2, Spack house Spack, etc., it's going to add a bunch of padding in here under the prefix, so that the thing gets installed and built for a much longer installation directory than it really needs if you're going to use the binary later. And so when you make binaries for other people, you want to do this. This is what we do when we build things in CI for our own environment or for our own build cache, which you can see at cache.spack.io. It's necessary if you want people to be able to install things into arbitrary paths. So you'll want to do this first in your build environment before you start pushing things around to different users. All right. And if you want to use this in CI, which folks have asked about, there is this setup Spack action that we've made that you can use. You can use that for, say, a Spack.yaml in a repository, and you can have it basically build your stack and push it to a build cache, and then keep reusing that build cache in subsequent CI runs with a simple action like this. And so here's a configuration that you would use on GitHub to get that done. There's a whole README here, so if you're interested in that and you want to accelerate your CI or use Spack to build your dependencies for CI, take a look at this and check it out. All right, and that's it for the build caches tutorial.
Okay, perfect. So the last thing that we're going to cover today in the tutorial is how you can go a little bit more advanced with Spack, using it both as a Python library or like an SDK for working with Spack packages, and how you can also work with it as the command line tool and do a little bit more scripting so that you can get some of those hashes out. You can write bash scripts on top of Spack to do some of your workflows. I think folks had asked about that a little bit yesterday. So the first thing that we want to do is uninstall everything that we've installed thus far today. Because we broke this up into two sections, there's probably not a lot to uninstall, but this just gives us a nice starting place. So we'll go ahead and run Spack uninstall -ay. And after we've uninstalled everything, we are going to make sure that we don't have GCC 12 as a compiler. Believe that I shouldn't for this. Yep. So we should be good there, but just in case you did have GCC 12 configured as a compiler, and then we'll go ahead and we'll install HDF5 to give us a few packages inside of our repository and installed packages so that we can start playing around with those. And then once this finishes, we'll also install zlib built on top of the Clang compiler. Sweet, and it went out from our local build cache, pulled everything, and we'll do a super quick Spack install zlib built on top of Clang, remembering the sigils that we learned yesterday for the % symbol being the built on top of a specific compiler. And now we should be ready to get started. So the first thing that we're going to cover here is some format strings inside of SpackFind. So we've used SpackFind a bunch throughout this tutorial. I'll demo it here a little bit. We've got regular SpackFind, which will pull out all of the packages and then the compilers that they built on top of. So you can see here we've got the packages that we built on top of Clang and GCC 11. If we wanted to have a little bit more specific output for this, so if you're working inside of a script and you want to be parsing some of that information, you can do SpackFind -- format, and then we can generate a format string here. So this, for example, would be the name of the package and the versions of the packages. But here, maybe we want a little bit more information. So we still want the name of the package. We want the version of the package, but we also want the first 10 digits of the hash. So here we can just write out hash. And then if folks are curious about the different terms here that you can use, like name, version, and hash, all of that is documented inside of the Spack documentation on Read the Docs. So you can see what variables that you have available to you. But if we go ahead and run this, it's a little dark because of the coloring, but you can see we have the name of the package, the version, and then the hash of, or the first 10 digits of the hash of every package here. We can build on top of this. If you're expecting to parse this information in a specific way, we can run spack find --JSON. And this is really just doing a format string that generates us something that is machine readable, such as, parsable by JSON. And so you can see here we have the hash of a package, the parameters. So it's, virtual packages. We've got, basically what it would be built with. So it's dependencies, the type of the dependency here. So we're doing a link dependency. So if you need to import your everything that you've installed with Spack out as JSON and then be able to use that, we have that option available to folks. So yeah, let's look at a specific example here for zlib. So we can see name of the package, version of the package, the architecture. So we built it on Linux, we built it on Ubuntu 22.04, and then we built for the x86 64 v3 target. We've also got the name of the compiler. So earlier when we asked to build zlibng with Clang, that's what we got out of here. And yep, then you've got their dependencies and the hashes of the dependencies there. If you want to, instead of working inside of Bash, work inside of Python and be able to do a little bit more manipulation on your packages, Spack, because it's a tool written in Python, also provides a Python interface. You can get at that Python interface by modifying your Python path and importing the libraries, but we create a nice wrapper around this called Spack Python to get you into a Python interpreter that has all of that already set up for you. And it works just as any Python interpreter would. So we'll jump into here. That's just to show you can exit back out of the interpreter just like you normally would. But once you're inside of here, we can run spack import. We're going to import the Spack object. And so this is, the specs that we have been talking about when you go install a package, when you add a package to an environment. The exact same language, we can reuse all of the sigils inside of here. So we're going to generate an abstract Spack for zlib, and then we're going to go and concretize it later on. So first of all, we'll do s, so that's just naming the name of our variable, and we're going to create a Spack object. We're going to create a zlib, but we're going to specify that the target should be x86 64 v3. And we'll go ahead and create that object. Now we can query this object in a number of different fashions. One of them is to ask, hey, is this Spack concrete? And it's going to come back to us and say, no, this is an abstract Spack. It hasn't been concretized yet. If we ask for the versions of the spec, it's going to say, hey, I'm an abstract Spack, so I haven't gone and I haven't figured this out for you. You didn't specify a specific version when you created me, so I could end up being all versions here. This is an unbounded version range. And if we asked for the architecture of the package, we're also going to get back something that looks like what we've asked for. We've asked for x86 64 v3, but it hasn't gone out and figured out the type of the system that we're running on yet. So Linux or Ubuntu is the distribution. So let's go ahead and concretize this object then. And to do that, we can just simply run s.concretize. And this is going to fire off the same, if you were to run spack install, all of those processes doing a concretization, this is the same. So here we can then ask, hey, am I concrete? And yeah, now that we've concretized, we're concrete. So asking again, let's say s.version, and whereas before we got that unbounded range, now we get a specific version back saying this is the latest version of zlib that we our, now that we've got a concrete spec out of it, we get the latest version since we didn't ask for a particular version. And if we come back and we ask for the architecture, so again, we'll grab the string and then s.architecture. We'll now see that this is fully filled out so that we get Linux, we get Ubuntu 22.04 as our distribution. And again, we still have our x86-64v3 as our target architecture for the compiler. You can compare specs. So let's create a new spec and we're going to call it zlib, or we're going to call it T, but we're going to give it the same abstract. And this time, right off the bat, we're going to concretize it. So that we can compare, we can say, is the concrete version of S equal to the concrete version of T? And 3. Well, we should have gotten something that was the same, but apparently they concretized slightly differently from each other.
You used concretize instead of concretized when you constructed T. And so you're comparing S to the value true that returned from concretize.
Yeah, just run S and then run T. You can see what they are. Okay.
Yeah, so if you change the T line to have a D on the end.
Oh.
Yeah. Concretized is the immutable version, right? It just returns the concretized version of the spec. It doesn't modify. And the other one returns none.
Yeah. Okay. So yes, now if we compare the two concrete specs, we can look at T here. We're comparing this against this and should get the same out of the two. Okay. So jumping on, that's how you can create spec objects. You can compare them. You can then use those comparisons to query what you might have installed somewhere else. So we'll add here and import spack.store. If we wanted to look at all of the available versions or all of the available information for our doc string from creating a query to our installation database, we can do that with help. And this will output basically, how we can interact with a query. So we're going to give it a query string. We can ask if it's installed explicitly or implicitly. So let's jump back into here and we'll construct one of those query strings. So we can create a query string. We're going to query for packages that are built with GCC. So let's call it our GCC query string. For our GCC query spec. So we'll construct a spec and we're just going to say built with GCC. And now we can query the database using that spec to return all of the specs that were built with GCC. And there is a small typo here this will be fixed in future versions, but we moved from Spack store.database to following better Python conventions, and it's now Spack store and then a global variable for the store that gets initialized when you're using Spack as the default place that we're installing packages into. So it'll be store.capital-store db query and GCC query spec. And now if we do this, we got back basically all of the specs that were built with GCC. Let's filter them though, and look for all of our specs, or all of our packages that were built with GCC, but that don't depend on impage. Oh, GCC spec instead of specs, because I pasted an S on that. Perfect. You can just look at the results of this if we want to make it a little bit prettier, we can import the Spack command library, which gives us this Spack command display specs. And that'll give us the nice, pretty output that you would expect. If we make, is it result?
You seem to prefer singular.
I do seem to prefer singular. So this gives us our nice, pretty output that you would expect from something like Spack find. So this is showing us everything that we installed that was built on top of GCC, but that does not depend on impitch. So we'll go ahead and exit the interpreter here and talk about how we can turn these into Python scripts. We've got about 10 more minutes left in the tutorial, and then we'll plan to hang around and answer questions for folks. So let's go ahead and create a little Python program. We're going to call it find exclude. So it is a little bit more fancy of a version of Spack find than we natively create. And I'll just copy and paste this in for time. But basically, we're importing that Spack object from the Spack library. We're importing our store so that we can query what we have installed. And then we're importing Spack command just as we did before to prettify the output a little bit. And then we're going to use argv1 and 2 so that we can pass arguments to this script from our shell. So we'll go ahead and we'll save that. And now we can see that if we run Spack Python and the name of our script that we created, we can say, hey, I want to look for everything that was built with GCC and does not depend on impitch. And I fixed it almost everywhere, but again, this is saying the Spack store moved to store.capital_store as that global. And so now you can see we get the same output from what we had interactively in the terminal there. If you are on, Linux, a couple of more modern operating systems will let you embed a more complex shebang line. But oftentimes we find that you have to have a binary that has a single name. And so we provide, in addition to Spack space Python, we also provide users. So if we were to make this executable shell, we also provide Spack Python as an alias for folks to that Spack space Python command. So if we go ahead and save this, we can see that after we make it executable, by doing a chmod on making it executable for find exclude, we can now run this just like we would any other program. And again, we'll look for everything compiled with GCC that does not depend on impitch, and we get the output that we expect. So, and we talked about this is the alias for a shebang line. Some systems will let you do something a little bit more complex, so you could have Spack and potentially pass a variable to it. But that's it. That's scripting with Spack. You can use many of the same internals that we use inside of Spack if you're writing in Python, and you can install packages inside of scripts. You can query your store. You can generate module files, set up binary caches, all of those. So if you get a little bit more advanced into the Spack world, we have people who have built tools on top of Spack, but this is probably a better way to say, start playing around with Spack scripting. If you find that there's functionality that's not in Spack that is, you feel like is pretty obvious, help contribute to the core tool, and you'll already be familiar with the same library and tools that we're using. So with that, I will pass it back over to Todd just to talk about the last little bits of the tutorial and maybe give a little bit of a roadmap from where we're going from here.
So I guess I'll cover this first. Yeah, thanks for coming to the tutorial. And this if the last that help you can get from Spack, we have a whole lot of resources that can hopefully help you if you want to contribute to the project or use the tool. So probably the best place to go, which most of you are probably already on, is Slack, because there's like 3,200 people on there at this point. And it's we try to very aggressively answer questions to make sure that people know how to use Spack. And I think in the past, when we've done surveys on this, some of our developers, like Greg, have gotten mentioned specifically as the most helpful things about the project, and that's from Slack. So please ask us questions there. If you're interested in contributing and you want to write packages, please do that. We can help you with the contribution process. Just ask. And there's also a contributor guide in the documentation. And there's other sections of the tutorial that you could try. Or if you want to go back to it, there's a container that'll always be available that you can use to do the tutorial sections with the build cache. The scripts are going to be there forever. And I guess we left this in from the last tutorial. We are hoping to have a BOF at Supercomputing this year. So join us at SC24. We're going to give this tutorial again. You may not need that. Unless you really want to rehash the same material. It'll be updated for the new version of Spack, so maybe there will be some significant new stuff. But we'll also have a BOF session that you could come to and talk to us. Right. And if you're interested in where the project is going, what we are working on most right now is finishing up something called compiler dependencies, and we talked about this at different points throughout the tutorial. Essentially, we are making compilers into first-class packages within Spack. So you may have noticed that you have to do a lot of fiddling with configuring your compiler locally, or even if you install a compiler with Spack, you have to go and set up config for it. We would like compilers to be first-class citizens, and doing that involves modeling all the runtime libraries and things underneath them so that Spack understands how to manage compatibility between different compilers. So we're very close to having that done. Compilers will be proper nodes in the new release. And this sort of continues a sort of long-term push at making it easier to use binaries within Spack. So the more of the sort of underlying compiler ABI dependencies we can model, the better we can do binaries. We're also working on ways to install bare metal MPI and GPU libraries on machines. You may have seen that like the NVIDIA containers can dynamically figure out like which CUDA runtime to load. We're working on ways for Spack to understand that sort of thing, so that if you install GPU binaries, we basically splice in your system CUDA or your favorite CUDA implementation, or install a compatible CUDA with the one that's on the machine. Similarly with MPI, we would want to basically allow you to make an environment, say here's an external MPI, and install from a build cache and have those things automatically sort of re-RPath to point at the system MPI. So we're looking at that. That's probably more of a next year kind of thing in terms of when it would make its way into Spack. We're hoping to have the build cache on by default, and that's sort of related to this compiler runtime modeling. We want to have libraries like libc and their compatibility, libc.c++, and so on, modeled in Spack. And we want to build with older versions of them for the build cache, so that we can essentially have a bunch of binaries available that are very likely to work on lots of different Linux distributions. So we're pretty close to that. We're going to continue to improve Windows support. And there's a lot of performance improvements in the pipeline that we're working on. So lots of exciting work ahead for the project. We had people ask, when would we go to version 1.0? At this point, I mean, we do try very hard to maintain backward compatibility between Spack versions. So I wouldn't say that just because our version starts with 0, it is version 22. So we've had quite a few releases. We try to maintain stability in the mainline. But for 1.0, what we are saying we would like are these things. We wanted the new concretizer. We did that. That's been in there for a while. We wanted production CI with build caches. We have that now. We wanted a production build cache that's hardened and it can be on by default. We're aiming for November for that. And we wanted compiler deps. And then the final thing that I think we want before 1.0 is we want to separate the package repo in Spack from the core tool, so that you can essentially point at a package repo that you want to use and continue upgrading Spack without having to necessarily upgrade the packages, or at least without having them as tightly coupled. You can point Spack at an older package repo now, if you want to, or a newer one. But it's not as smooth as we like it to be. So we'd like to basically minimize the coupling between Spack and the packages and have them able to sort of live lives of their own without quite as much tight updating required between the two of them. And that's really this is really the compatibility promise that we will be making with 1.0 is not to break the package API. Right now we rely, especially for things like compilers as dependencies and big changes like that, on being able to change the packages as the tool evolves. And we'd still be able to do that with a stable package API, but not quite as much. And so that's what we're looking for. So we're hoping to do 1.0 sometime next year. And that's it. Any other questions? All right. Well, thanks to everybody for coming out to the tutorial, and I hope you enjoyed it.